This is optical isomerism, something which strikes me as being fantastically wonderful. Why? Look at these two molecules on the screen. We have a cyclohexenyl ring. We have a methyl group written as CH3 and H3C on the top. We have a wedge, which is the one that's sticking out of the screen here. This wedge means it's coming towards me, and the dashed line means it's going away from me. So there's a hydrogen going away on this carbon atom on the cyclohexenyl ring, and there's a carbon coming towards me, pointing out of the screen. An ethene bridge, if you like to call it that here, an ethene bond, and another methyl group here. So this carbon here can see if it looks around, put your helmet on, go in the ring, have a look around. We have here a hydrogen. This group here relates as a propene sort of subchain, and we have the rest of the ring here, and we've got a double bond up there. So this is asymmetric. We have 4 different groups. You can see 4 different groups. We have asymmetry, and we have something called chirality. Now, we know those kids that used to like, what's the difference between these two diagrams? I liked those. So let's have a look. This one, methyl, methyl, same. Carbon, carbon, double bond. It's on the different side, it's on the opposite side, but we'll just park that for now. Cyclohexenyl, hydrogen, this propene group. Hang on a minute. So this propene group here is stuck out to the page, and this propene group is stuck out to the page, but on the opposite side. And this is on the opposite side. If I was circling, going, what's changed? I'd be circling here and here. That'd be giving me 1 mark. And the hydrogen, although behind, is on the opposite side. Okay, these are what is called a pair of enantiomers. What difference does it make? Well, it makes a lot of difference. First of all, nature loves to be left-handed. What does that even mean? We'll cover that shortly. This molecule in your mouth tastes different to that molecule. The one on the left clearly tastes of lemons. Your tongue would recognize the architecture of that molecule as it docked into the taste receptors on your tongue as lemons. However, you swap around the side on which the hydrogen and the propene chain are, then it tastes of oranges. It's just, wow. And this is the phenomenon of chirality and optical isomerism. So there's quite a bit of jargon here. Here I have, this is carbon, this is bromine, this is fluorine, this is chlorine, this is hydrogen. Again, we've got carbon in the middle. 1, 2, 3, 4 different groups. 4 different groups means we have asymmetry, and we can have optical isomerism. What will be the name of it? Well, it's alphabetical order, isn't it, as you know? So that would be bromo, chloro, fluoro, methane. So I thought it'd be fun to build another one here, next door to it. There's the the carbon to bromine bond, which is here. The carbon 2, that's the bigger one, so that's the chlorine. Fluorine, that's the smaller one, and a little bitty hydrogen up there. Now, let's just sort out the geometry of that. There we go, they look a lot better now. And we can spin them around. Aha, they are both. Bromo, chloro, fluoro, methane. But are they the same molecule? No, they are not, because I cannot superimpose. If I line up my bromine, doesn't look quite right, let's idealize that one, there we go. Bromine and my bromine. My hydrogen is stuck into the page here and stuck out of the page here. Okay, maybe I can just flip that 180 degrees. Of course, it's going to do the same on the other side, isn't it? If I could just manipulate one on its own, which I don't think I can do on here, we could move that hydrogen to stick out here. If we did so, flip that around in your head. Flip it around in your head. Are they the same molecule? No, because the chlorine and the fluorine are on opposite sides. They are what's called non-superimposable. And you're thinking, why is this important? This is very important, because nature thinks it is important. You are tasting everything that you taste on your tongue because something is a specific connectivity to give a correct optical isomer for your body, your tongue, to sense it. So, we don't need a molecular modeling kit, but let's have a look. We're going to look at stereoisomerism, optical isomerism, enantiomers, what's the meaning of the word chiral, and what's the meaning of the term racemic. Let's try and get this done in 20 minutes. Okay, here's a boy. Hi, boy. He's got a pair of sneakers on, blue shorts, red shirt, and kind of a nifty little haircut. His left hand's saying hello, his right hand's kind of behind his back. Okay, let's rip his head off and swap it for his foot. Why? Because we can, he's a cartoon. Haha. Now his foot is coming out of his head socket, his neck, and his head is on the end of his foot. So rip his head off and swap it for his foot. This boy is now a structural isomer. You might not like it, you might not enjoy it, but he is. He's a structural isomer. Don't worry, he has no feelings. He's a cartoon. Back to the original boy. Watch carefully what happens. Aha! What happened there? Well, you all saw that on his left hand that's saying hello, somehow his thumb moved from the top side of his hand to the bottom side of his hand. Okay, his boy's hand is now a stereoisomer. Oh, there's a lovely word. Stereoisomer of the original. Back to original boy. What we're going to do to him now. Hands up, punk. Ah! This boy is not an isomer of the original. We didn't have to break any bones. So you have to break some bones on your cartoon boy, not a real one. Break some bones on the cartoon boy. Then you have formed an isomer. So what's the difference? Well, clearly his foot is in his neck and his head is on his foot. Unbelievable. But this is structural isomerism. Okay, you could have butane 1-ol or butane 2-ol. I don't know why my voice just went up then. It just did. We also have, here's the boy with his thumb, got that right way around, thumb. There we go, and it's going to flip to the other side. Aha! Okay, so we've got a different configuration for boy with his thumb down, left hand thumb up, and then the end is not an isomer, he's just going huzzah! So, we have EZ, Entigen, Zummersen, forgive my German, something like that. That's the cis and trans, and the E and Z. Carl Ingel Prelog system, saying lots of jargon already. Welcome to the world of stereoisomerism. And we also have optical isomerism. So your hands are a pair of enantiomers. Let's say that word again, enantiomers. These, if I keep them like this, my thumb is always on the other side to the other thumb. So they are non-superimposable. A chiral molecule is a molecule with no plane of symmetry. You can't put a mirror down the middle of it, reflect one side to make the other side, and remake the whole molecule. So chiral molecules, a chiral molecule has a non-superimposable mirror image. You cannot put them on top of each other. For that to happen, you need to have 4 different atoms or groups attached, and as we saw at the beginning, that could be a ring as well as a straight chain. Chiral molecules exist as a pair of enantiomers. Now for stereocenters, that's a point with 4 different groups attached to it, or a carbon atom with 4 different groups attached. For IB, we're going to stick to 1, but you can have 2, 3, 4, you can have many chiral centers in one molecule. Next bit of jargon, a racemate or a racemic mixture has a 50-50 mix of a left-handed molecule, come to that, and a right-handed molecule. If you have 50% left and 50% right and you mix them together, you get 0 rotation. Let's have a look. So here we have alanine, a basic amino acid. Okay, we have the carboxylic acid functional group on the right-hand side here, and we have the amine functional group here. Looking at the molecule, where would it be chiral? Where are the 4 different groups attached? Well, never a methyl group because these 3 hydrogens are the same. This carbon atom here, what can that see? I'm always thinking about what can it see. When I put my helmet on inside that chain, look around. I see hydrogen, I see NH2, I see CH3, and carboxylic acid. So this carbon atom here is chiral. So this methyl group can flip So that side, is this a mirror image? Yes, it is. We have L, which stands for levorotatory. That's not on the IB syllabus, but that's why it's L. And D is dextrorotatory. Not on the IB syllabus, but it's nice to know. Okay. They are superimposability. If they can perfectly overlap, that means they are the same enantiomer. But if we try to mix these together, they are not. Okay. You can rotate the molecule, but you can't break the bond. You can't rip off the carboxylic acid group and stick it on the other side to make this superimposable. Nature cannot do that. Here's a lovely molecule. They often think of these as kind of a little puppy dog or a little Dalek that's looking at its mirror image in the mirror there. It's gazing longfully at its partner. Oh. And here's the mirror image come to life. There it is. Okay, are those the same molecule? Put your three-dimensional abstract reasoning on. Pick up that front molecule, rotate that hydrogen with the oxygen. Where is the green atom? I guess that's chlorine or fluorine or something. It's a halogen. Where's the green halogen going to be? If I pick up that molecule, get the hydroxyl group, which is at the top, spin it a little bit, probably through about 90 degrees to sit on top of that one. The hydrogen at the back would sit on the hydrogen at the back of that one at the back, but the green and the silver would be in different positions. They are enantiomers. Okay, so these are non-superimposable. They do not superimpose. So that carbon atom, the carbon atom, is chiral. But hey, so how many different groups are there? 4. You need 4. Is there a plane of symmetry? No, there is no plane of symmetry. I cannot put a mirror anywhere in there, reflect the other half, and see the original molecule. As well as objects, we can also look at molecules. And here we have some items. Which ones have a plane of symmetry? Well, the vase. I could put a mirror in the middle of the vase and reflect the vase. The spoon looks pretty good. What about the screw? Can I put a mirror down the middle of the screw and reflect the image of the screw to reform the original screw? Aha. What did you think? So the non-chiral objects. Okay. Achiral, mirror image there. We're on the sunglasses. It's the same on both sides. The vase, straight down the middle, plane of symmetry. The spoon, straight down the middle, plane of symmetry. So they're achiral, non-chiral objects. A chiral object is a pair of gloves, the same as the hands, right? Cannot, same as the gloves. The shoes, one's left, one's right. Clearly chiral, cannot be superimposed. And the screw, the thread would go in the opposite direction to the real direction it was originally, so that is a chiral object. We've been talking about left-handed and right-handed molecules, or levorotatory and dextrorotatory molecules. Levo means left, and dextro means right. And the left and right is as a result or as a consequence of the sample of that enantiomer being placed in the path of a polarized light source. So if you put your sample into some polarized light, the light will be rotated in either a right-hand direction or a left-hand direction, depending on which enantiomer, which version, which side of the mirror you are looking at. So the transverse nature of light waves makes it possible to see it changing, and this is measured using a polarimeter. In the olden days, you had to know the steps in the polarimeter. Now the IB don't care. So just know that a polarimeter tells you whether it's left-hand or right-hand rotation. Okay. Different enantiomers rotate the plane of polarized light in opposite directions. If they are different, a pair of enantiomers of the same molecule, they'll rotate to the same degree, but in opposite directions. So if one's minus 42 degrees, the other one will be plus 42 degrees. Clearly, it's the same molecule, just different connectivity. So they have similar chemical and physical properties, but biologically, they have massively different properties. Okay, very good. To make them, you need to have a symmetrical synthesis. So if you are a pharmaceutical company making drugs, synthesizing pharmaceuticals. You need to be keenly aware of which enantiomer you are making. Ibuprofen, a common analgesic, exists as enantiomers, and it turns out that when they first manufactured it, they got 50-50 the racemic mixture of the left and the right, but only the left actually produced analgesic or pain-killing effects, but the right didn't. Thankfully, the right is not toxic, which is not always the case. Sometimes, with devastating consequences, one of the enantiomers is actually highly toxic. So here's methanol. Can that be chiral? No, it's got 3 hydrogens. So 3 groups the same, 1 group's different, which is the hydroxyl. You cannot have an enantiomer of that. But we know the wedge coming out is pointing towards us, the dash going back is going into the board. There's the ball and stick model. But not all molecules are as simple as methanol. On here we have a selection of molecules. I suggest that you pause the video, see if you can spot the chiral carbon atoms in these molecules, and carry on playing. See you in a minute. Welcome back. So, to bromobutane. Is there a carbon atom where there are 4 different groups? Well, here, I'm going straight to the answer. Bromine, there's a hydrogen here because it's a skeletal formula. Methyl group there, ethyl group there. So it sees ethyl, hydrogen, methyl, bromine. So yes, that does indeed have a chiral carbon atom on that carbon connected to the bromine. Aspirin. Double bonds will never show chirality, so you can ignore all the double bond O stuff, and we have a look, and there are no carbon, because even in the ring here, on the phenyl ring, it's double bond, alternating double bond, isn't it? Double bonds, methyl, no hydrogen, so no chirality. Thank you for the aspirin tablet. Aspartame. Let's have a look at aspartame. Is there anywhere here? Well, that's double bond, so no. This is 2 hydrogens, 2 groups the same, so no. Well, this looks kind of promising because it's got an N, it's got an amino group, it's got a carbon to a carboxylic acid, it's got a ketone, it's got an amide here, a carboxamide group here, so that looks pretty good. What do we think? Yes, there is 1 carbon atom, and there is the second one. The other dead giveaway, there were 2 big fat wedges here, suggesting that you have optical isomerism. Can't be here because it's CH2 and all this double bonded stuff. Just forget it. It's never going to be chiral. And there is some artificially sweetened Coke. Chloroethanoic acid. Double bond, forget it. 2 hydrogens, forget it. No chiral carbon atoms. 2,3-dimethyl pentane. 2 H's, no. CH3, no. CH to methyl to this. Oh, that looks kind of promising, doesn't it? Right there. Propene, double bonds cannot show chirality because you need to have 4 different groups. With a double bond, there are 3, so no chiral carbon atoms. Tyrosine, produced in the glands in your throat. Where's the molecule gone? There, okay. Where is it? It's going to be here, isn't it? Because the CH to NH2, carboxylic acid, all this gunk here in the phenyl ring with the hydroxyl group. So this here is the chiral carbon atom. Binol, what a beautiful, beautiful molecule. Double bonded everywhere, no chiral carbon atoms. Thalidomide, this is the drug which produced teratogenic birth defects, does of course have enantiomers, which became apparent as time went on. And there on the ring we can see carbon connected to nitrogen, connected to a carbonyl, which is a carboxamide, connected to an alkane, a cyclical alkane group here, and a hydrogen, so 4 different groups. Thalidomide. Glucose, look at all those dashes and wedges. That's just going to scream to you, yes, that these all have optical isomers. And every one of these positions here on glucose, look at that, 1, 2, 3, 4, 5 centers of chirality. And glucose is L or D, depending on which isomer, enantiomer you have. Phenylalanine, another amino acid. Benzene ring, forget it. CH2, forget it. This looks kind of promising here, doesn't it? Of course it does. Amino group, carboxylic acid, and then the gunk to the left-hand side. So amino acids are chiral. Glycine, NH2, no 2 the same. CH, no double, no chiral carbon atoms. Tetrahydrocannabinol, this is the active ingredient in cannabis, marijuana, THC. You can see dashes and wedges straight away. That means that there are going to be two. Clearly these are the two here. The dash and the wedge is the clear giveaway. Cytosine, one of the bases in DNA. We can see there's a cyclopentyl here. So that's 1, 2, 3. I think that was pretty promising. There, and there. Yes. So 3 chiral centers in cytosine. Glycerol, otherwise known as water. We're going to methionine now. Oh, sorry, I missed out methionine. CH2. Oh, this looks promising, doesn't it? There, yes. Very good. Glycerol, propane 1, 2, 3 triol, CH2, CH. Oh, that's no, cannot, because the symmetry. That's CH2 to OH, CH2 to OH, symmetrical. No. And cholesterol. Look at all those dashes and wedges. Just put a lovely star next to each one of those dashes and wedges. It's to give you dashes and wedges in a question to say yes. Yes. And clogs up your arteries and gives you heart disease and an early death. So, 3 facts about chirality. Okay? It turns out that on planet Earth, and as far as we know in the universe, then nature is predominantly, almost exclusively, the left-handed enantiomer of amino acids. We don't know why. There are a few exceptions. So no one has a Scooby-Doo. Why? Okay. There are chiral molecules without chiral carbon atoms. Okay, so if it's got no plate of symmetry, then, yeah. And steric hindrance prevents rotation of the carbon-carbon bonds that holds 2 naphthol. You want to see naphthol? Look at that. So these are locked. Look, so steric hindrance, that's just going to interact, it's going to repel. So they can't rotate, so it's fixed. DNA is chiral. Okay, DNA contains chiral carbon atoms, but of course it's a helix, as we all know. And then there was the very tragic story of thalidomide, where the wrong enantiomer gave teratogenic birth defects, and babies born with disabilities, and that still goes on to this day. There's 3rd, 4th generation thalidomide children being born. That people guess and theorize about the actual interaction of thalidomide with DNA and that caused these defects. No one actually knows yet. Okay, so it's actually come back now as a HIV therapy. If you don't prescribe it to a pregnant person, then it's kind of okay. But clearly, a lot of research is needed further on this one. So we don't actually know the mechanism of teratogenicity. There we go. If you can say that first time, congratulations. Well done. And there endeth today's little lecture on the beautiful world of optical isomerism. I'll leave you with that gorgeous image of lemons and oranges. What a fantastic thing. Thank you very much for watching. Smash that subscribe button. Go and eat some vitamin C rich fruits and think about the enantiomeric dispersion between the flavours of your sensors of your tongue